Hello, this is our presentation on our research paper which is titled Technical Survey on Cloud Scalability. This will be presented by Group 7. Scalability in cloud computing is the ability to quickly and easily increase or decrease the size or power of IT resources to meet changing demand. A subdomain of cloud scalability is cloud elasticity, which is the system's ability to expand and contract based on workload demands. In the past few years, a lot of state-of-the-art research has been conducted on cloud elasticity. The last review paper that focused on the whole aspect of cloud elasticity was published way back in 2015. After that, a few review papers were also published, but they focused on only a particular aspect of elasticity. So there's a need for reviewing research conducted on elasticity from 2015 to 2022. This review is necessary to overcome the challenges and limitations of state-of-the-art approaches for providing cloud elasticity and also for providing a path for future research directions on cloud elasticity. Here we will present a technical survey on cloud scalability. We will gather approximately 25 research papers that pertain to scalability, specifically elasticity, and the different methodologies, algorithms, and formulas, as well as current problems with suggested solutions.
Hi everyone, my name is Oluwakemi and I'll be talking about the motivation of a paper. Elasticity property is crucial as it enables cloud deployed applications to meet performance and cost objectives in the face of variable workloads. So with cloud elasticity, an organization does not need to pay for capacity that remained unused. It also helps to avoid over-provisioning or under-provisioning resources, which could lead to the inability to meet up with existing demands. With various research established about cloud elasticity, there are still many issues about elasticity that needs to be addressed. And we have such open issues about cloud elasticity. We have them listed here. We have the interoperability, we have hybrid solutions, we have threshold definition, we have an optimal trade-off between the user's requirement and provider's interest. For instance, it is difficult to use in multiple clouds to provide resources due to the lack of standardized APIs, and each cloud platform has its own unique ways of in which they actually communicate with client applications, user interactions with the cloud. So this paper will provide a survey on cloud computing elasticity mechanism or algorithms available today.
My name is Carl, and I'll be going over our existing literature and challenges. Covered a paper, Cloud Performance Modeling with Benchmark Evaluations of Elastic Scaling Strategies. And what this really touches on is first, it goes over some of the real world problems that cloud computing scalability faces today, specifically trying to put qualitative metrics on what really is elastic and how can we measure in terms of raw numbers. Is a system truly elastic and how elastic it is? It does this by coming up with a set of proposed metrics and how they can be recorded. It then tries to measure these against three of the popular models, IaaS, PaaS, and SaaS. Recorded the metrics, compares them, and kind of had five main takeaways here. Number one is that, like I said before, the industry really needs new and clear-cut ways to record if a system is truly elastic. And furthermore, it emphasizes in order for a service to be successful, it needs to be scalable. Because if they're constantly facing growth issues, not being able to have quality service as they expand, that's going to reflect poorly on their customer base, and vice versa. If they're over buffing their servers and they're always pretty much overstaffed on their server resources, they're going to be consuming a lot of costs and they're not going to be and kind of in for the long game. They're not going to be profitable. And then, like I said before, it compares those three different models and also compares the cost effectiveness of scaling up versus scaling out. And what the pros and cons of each one, and really the long-term takeaway from this is that modern day industries need to be more proactive with adopting elastic models on their server infrastructures to maintain longevity for the points I previously discussed here about maintaining as low cost as possible while being able to consume the amount of growth and the rapid growth that these companies face today, particularly with these e-commerce and internet avenues that are so popular nowadays.
Research objective. The recent acceleration in customer demands for cloud-based services leads to rapid advancement in cloud technology. So to improve the quality and performance and also to reduce the cost of providing cloud elasticity, a lot of new approaches and algorithms have been proposed in the recent past years. So the main objective of our research is to present a comprehensive literature review of existing recent works on cloud elasticity. So we will discuss recent approaches and algorithms on cloud elasticity along with their benefits and challenges. And finally, we will suggest some future research directions on cloud elasticity.
Our next research paper is High Scalability for Cloud-Based IoT M2M Systems, and here are the authors. According to the authors, there are two traditional approaches for system scalability, but these two approaches are not appropriate to provide optimal results for IoT M2M systems. This is because IoT M2M systems generate high volumes of traffic, and this traffic can be burstily unpredictable and uncontrollable. The authors introduce a new approach for cloud-based IoT M2M systems that improves resource utilization and energy consumption. One of the major differences between the proposed architecture and the cloud-based system scalability is the complexity of them. The proposed one introduces a master node which is able to communicate between the load balancer, which distributes the traffic using a balancing algorithm, and the network service capability layer, or NSCL nodes, which constitutes the actual IoT M2M computational power. The master node then takes care of specifying the amount of NSCL nodes based on information provided by the nodes themselves and the load balancer. This information can be the amount of traffic, CPU utilization, etc. The master node uses a modified version of the cooperative load balancing algorithm in order to determine its results. In their results, they found that their method improved the response time by 46% and their energy consumption went down by 14%. They do mention that they would like to test more on different scenarios, since this was only tested with a high load scenario and a low load scenario. The next research paper is Distance and Traffic-Based Virtual Machine Migration for Scalability in Cloud Computing, and these are the authors. So most organizations are shifting their business to the cloud. So we all know the cloud in reality are huge data centers located anywhere in the world. And these help to minimize the operational cost. But right now, most algorithms focus on energy consumption and network traffic between these data centers, and they do not focus on the user and providing the fastest results. The authors provide a new algorithm which aims to minimize the round trip time, or RTT, for the client request, allowing for faster results. It is called a VM migration approach based on distance and traffic. So the proposed architecture consists of different modules. These include the user request, the load balancer, in charge of redirecting the request to the appropriate VM, the physical machines which host the VMs, and the dynamic allocation of VM. The concept is simple: migrate the VM to another data center which is near to the client and that has less traffic in order to improve the RTT. The algorithm proposed attempts to place VMs on the physical machines that have the lowest RTT for request, and it gets done by organizing the candidate's physical machine in ascending order by according to the minimum distance and minimum traffic in the data centers. The authors compare the results to other two algorithms, the traffic-aware VM placement algorithm and the remaining utilization algorithm. They found that the proposed algorithm outperformed both when it came to average RTT. And in future works, the efficient utilization of cloud resources as well as the reduction in power and energy consumption could be considered, the authors mentioned. The next paper is scalability of mobile cloud storage, and here are the authors. The main issue related to data management are the cloud scalability of data and storage data in mobile cloud storage, or MCS. It is important to maintain the scalability even if users access the data file with many cloud storage services at one time. The authors here want to enhance the scalability in handling several data in MCS environment. The scalability test was conducted by comparing different load levels, which were data load level 1 to data load level 5. For example, data level 1 consisted of data files, which were data 1, 2, 3, 4, and so on. Then data 1.1 and data level 2 was referred from data 1 from data level 1. Data 1.1.1 and data level 3 were referred from data 1.1 and data level 2, and the others follow the same flow, as you guys can see from the graph. When creating a scalability test, it is important to scale up in increments. Small loads ensure the system functions as it should be on a basic level. Medium loads test if the system can function at its expected level, and high loads test if the system can cope with a high load. The scalability was measured based on the total number of responses. 5 data labels were being used in this research to analyze the total response time with or without the prefetching. In addition, the total response time based on DT algorithm was also recorded. Based on table 1, it was proven that using prefetching was effective compared with traditional MCS without the prefetch. The scalability test was successful as it required less total response time in accessing the data even at a high data level. The performance of prefetching was measured based on the latency per page ratio that was calculated to evaluate the latency on the MCS. The results showed the latency was low even at a high data level. Besides, precision and recall were used to measure the effectiveness of the performance of prefetch. The next paper is end-to-end elasticity control of cloud network slices, and here are the authors. Current elasticity control mechanisms proposed for cloud slicing only consider cloud type measures. The authors introduced the elasticity in cloud network slices, or slots, which aims to extend the horizontal elasticity control to multi-provider scenarios in an end-to-end fashion, as well as to provide a novel vertical elasticity mechanism to deal with critical insufficiency of resources by harvesting underused resources on other slices. The cloud network slicing approach from slots provides an end-to-end view involving a set of physical and virtual components such as cloud servers, network nodes, VMs, etc. The slots proposal encompasses the design of a functional architecture by presenting different functional blocks and internal subsystems that interact with specific interfaces to perform different functions. The main blocks are Cloud Network Control Plane, DC and WAN Control Plane. Each one has its own components and they do different functions. The Cloud Network Control Plane consists of the slice constructor, the slice descriptor, slice resource orchestrator, and slice monitoring, as well as the slice database. The DC control plane consists of Cloud Slice Controller and the VIM, and then WIN control plane consists of the Network Slice Controller and WIM. The model that Slots applies for elasticity control is unique in orchestrating a way that manages resources between donors and recipients in cloud network slices according to the recurrent patterns along with committed rates. The slot solution was evaluated through real test bench prototypes to obtain accurate information. Proof of concept analysis confirms that the slot's elasticity control scheme complies with the proposed architecture and addresses the end-to-end cloud network slices. As slots is an ongoing project, the authors will continue to focus on studying and developing additional assessments, enforcements, and control mechanisms, and tailor them to improve the reorchestration of all the resources that support the cloud network slices. Moreover, they mentioned that they need to introduce new functions to deal with horizontal elasticity. Finally, the last paper that I included was towards bridging the gap between scalability and elasticity, and here are the authors. So the authors discuss the creation of a bridge that will eliminate the gap between processing long-term and short-term workload variations when it comes to scalability and elasticity. They introduce a three-layer architecture inspired by self-adaptive systems for self-managing scalability of multi-cloud systems. These layers are a long-term layer, mid-term layer, and short-term layer. Now, when it comes to the mid-term layer, the Usage Evolution Manager selects a usage evolution profile based on the current workload and context of the running system. The workload predictor predicts what the workload will be at the time t plus 1 based on the workload at the current time t. The workload comparator compares the current workload with the predicted one. The architecture selector selects the most suitable architectural model from the set of possible architectural models based on the current and predicted workloads. And the deployment selector selects the most suitable deployment model based on the corresponding architectural model. The authors concluded that the realization of this project was still ongoing at the time of publishing, and it was a joint work between CloudScale, Moda Clouds, and Passage projects. Future works that were mentioned were finalizing an implementation and validation of the proposed approach.
Scalability, Elasticity, and Efficiency in Cloud Computing by Sebastian, Enrique, and Stephen Baker. The authors carried out a systematic literature review to tackle the lack of guidance on existing definitions and metrics for scalability, elasticity, and efficiency. So there are multitudes of definitions and metrics available in existing literatures, and these properties are unstandardized, whereby we have different people with different definitions. So the authors collected common concepts in existing literatures, and they use it to differentiate the metrics, cloud characteristics, and roles. So they make use of 20 results were selected from the initial 418 results from the systematic literature review survey that they conducted for this literature review, and they make use of 2 research questions, which include targeting how to define scalability, elasticity, and efficiency. Then the second one is the metrics for the 3 properties that are listed above. So their report defines scalability, elasticity, and efficiency metrics. And the report of the research questions defines scalability as the ability of a cloud layer to increase its capacity by expanding its quantity of consumed lower layer services. And also, the metrics for scalability are generally not restricted to a particular role. Their report also defined elasticity as the degree a cloud layer autonomously adapts capacity to workload or time. And lastly, efficiency was defined as a measure relating demanded capacity to consumed services over time, and the metrics measure the number of the lower layer services over the time. So the authors recommended that their metrics can be used, the definitions can be used by solution architects to analyze the quality of cloud applications. And what I found missing in this paper is that the paper did not prove the elasticity metrics, as it was actually like mentioned as part of their objective of this paper. Measuring and testing the scalability of cloud-based software services by Amro and Peter Andrews. So the authors proposed technical measurements and metrics for the scalability of cloud-based software services. And that means that they actually make use of metrics that addresses volume and quality scaling for evaluating cloud-based software services, scalability performance. So the metrics they use are based on principles of proportional scaling of the service volume and constant provisioning of the service quality. And these are actually used to define the difference between the real and ideal scaling curves for both the volume and quality scalability. And the author proposed how technical metrics can be integrated with their earlier utility-oriented scalability metrics, which these frameworks were proposed by another author, which is Liu H. The paper demonstrated the application of the metrics to a concrete cloud-based software services using the Amazon EC2 cloud. Their result shows how the metrics can be used to identify differences in the behavior of the asset system. And what I see to this paper is that they actually use two scenarios to explain what they want to achieve, and which actually shows that if they make use of wider range scenarios, that's going to give us a better and deeper understanding of how the proposed metrics works on different scenarios. Elasticity in Cloud Computing by these authors Yahya, Fawaz, Nabil, and Philippe. These authors represented a meticulous analysis of elasticity approaches, and it is the very first survey that addresses the elasticity of containers. So the authors also propose a concise definition of elasticity, and they mention related concepts to elasticity such as scalability and efficiency, and approach to measure elastic systems. So from their point of view, elasticity in their work was defined as the ability of a system to add and remove resources to adapt to the load variation in real time. So the paper also proposed a classification and taxonomy for elasticity solutions based on the configuration, scope, purpose, mode, method, provider, and also the architecture through study and analysis of different industrial and academic elasticity solutions. As the container-based virtualization have evolved dramatically, the paper discussed container technologies and their pros and cons. The makers of Docker and Rocket were mentioned in the paper as the most recent used container technologies due to the enhanced features. So the paper made justice in analyzing and discussing the definition of elasticity and its related terms. The paper also addressed the open issues and research challenges about elasticity of containers in cloud computing. Another paper that I did was a model-based scalability optimization methodology for cloud applications by this author, Jacobo, Thomas, and Ingrid. So this author presented a methodology that allows users to understand the best way to configure the scalability of the application to be deployed on the cloud platform. So this was done by using an existing service-oriented framework to dispatch car software updates. So the writers actually discouraged the direct optimization of the entire system, and they provided 3 steps in their scaling optimization methodology as a solution. From the diagram here, it shows that the first step is system profiling and analysis. So this means using worst case scenarios, e.g. Queen theory, to understand what parts of the system can be simplified. The second step is simplified model creation. So this step creates a simple model with fewer parameters to tune, and the last part, which is the third step, is scaling parameters optimization. So this uses automatic parameter configurators tools. These tools rely on machine learning. So these tools were built using machine learning techniques. The author were able to apply their proposed methodology to a service-oriented framework, that is the CAR software framework that was used to deploy, or that was deployed in the cloud. And the future works of the authors will be to analyze bigger and complex systems and go beyond the current reactive scaling and study different proactive strategies. So these authors reported their understanding of their recent and future challenges in scalability and dependability challenges of computing on a massive scale. The author introduced a data-driven analysis methodology to describe the resources, workload models, and tracking performance constrictions in a massive scale distributed computing environment. The fundamental challenges were examined and were analyzed, and also the solutions were provided to tackle the challenges. The paper integrates their solutions with their data analysis methodology to establish a standardized approach, and their future works include innovating methods and mechanisms for computing platforms that will provide strong support for big data and Internet of Things applications.
The title of the reviewed paper is Enhancing Performance of IoT Applications with Load Prediction and Cloud Elasticity. The study was conducted by Rodrigo da Rosa Righi and ETAL, and it was published in Future Generation Computer Systems in 2020. In this paper, the author presented ProPilot, a proactive elasticity model that combines cloud and high-performance computing to address the IoT scalability problem in a novel EPZ global compliant architecture. So the author uses autoregressive integrated moving average, ARIMA, and weighted moving average to predict the IoT load behavior. And based on this load behavior, the system changes the elasticity. The application areas where this method or algorithm can be used are IoT, electronic product code, and information services. And for this approach, they use EPZ Global Compliant Architecture. And for evaluating their method, they uses the metrics average response time and average request per second. And they found that their algorithm can gain 300% in comparison to a scenario with no elasticity support in terms of average response time, and 36% gain in terms of average request per second. One of the limitations and challenges of their proposed algorithm is that their model requires more energy than non-elastic models. And also, their model needs to evaluate on more real-time IoT traces data. The title of the reviewed paper is Plasma, Programmable Elasticity for Stateful Cloud Computing Applications. The study was conducted by Bo Sang, ETAL, and it was published in EuroSys, Proceedings of the 15th European Conference on Computer Systems. In this paper, the author presented a programming framework for elastic stateful cloud applications called Plasma. The full meaning of Plasma is programmable elasticity for stateful cloud computing applications. So here they use elasticity programming language for describing elasticity behaviors and elasticity management runtime for profiling runtime behavior of actors like location, resource uses, and their interactions. The application area of their algorithms is for stateful cloud applications such as the distributed file system, multi-tier web application, microservice application, and multiplayer online games. They used the Amazon AWS and Aeon technology for these algorithms. And they use the evaluation matrix latency to evaluate the performance of their algorithm. They found that they implemented 10 different distributed cloud applications using Plasma, such as Metadata Server, PageRank, and B+tree implementation. And they found that Plasma significantly improved their efficiency, achieving same performance as a vanilla setup with 25% fewer resources or improving the performance by 40% lower latency compared to the default setup. One of the limitation of this approach is that their model introduces second-level programming languages that makes the model complex than the traditional model. The title of the reviewed paper is Exploring Publish, Subscribe, Multi-Level Cloud Elasticity and Data Compression in Telemedicine. The study was conducted by Vinicius Paco Rodriguez and ETL. It was published in Computer Methods and Programs in Biomedicine in 2020. In this paper, the author proposed a cloud-based publish, subscribe, PubSub model called PS2DCOM, which employs multi-level resource elasticity to improve the performance of digital imaging and communications in medicine. So the author uses to reduce the demand for network resources. They used the 3 different algorithms: delete, LZMA, and BGIP2 for image compression. And they use the multi-level cloud infrastructure and cloud-based publish subscribe model to implement this method. The application area of their proposed methods are medical image data and telemedicine. For this implementation, they uses Amazon AWS, Amazon EC2, Amazon RDS, RabbitMQ PerfTest technology. And for evaluating their methods, they uses the execution time and messages per second as evaluation matrices. The general efficiency gain is approximately 35% in data sending and receiving operations for their method. One of the challenges of their method is that they only evaluated their method for a small system, but they need to know the performance of their model when the system will be much larger. Also, integrating their model into enterprise content management, ECM, is challenging. The title of the reviewed paper is Model-Driven Elasticity Management with OCCI. The study was conducted by Yahya Al-Dhurairi, ETL. It was published in IEEE Transactions on Cloud Computing in 2021. In this paper, the author presented MoDemo that can support complete modular elasticity solution. Their proposed model supports both vertical and horizontal elasticities on both virtual machines and container virtualization technologies. The application areas of their proposed models are vertical and horizontal elasticities, and for virtual machines and container virtualization technologies. For implementing their methods or approaches, they use Open Cloud Computing Interface, OCCI, Amazon AWS, Microsoft Azure, and Google Cloud Platform. They also use Flask for applications and Redis for database. They showed that their model supports all the elasticity policies found in AWS, MS, Azure, and GCP with some suggested improvements. One of the challenges or limitations of their methods is that their model introduces additional overhead for runtime support of reconfiguration. Also, this model does not provide any synchronization between 2 different elasticity policies. The title of the reviewed paper is Equilibrium, an elasticity controller for parallel tree search in the cloud. The study was conducted by Stephen Kehrer, ETL. It was published in the Journal of Supercomputing in 2020. In this paper, they proposed an elasticity controller that reasons about the scaling behavior of the parallel system at runtime, and it can dynamically adapt the number of processing units according to the user-defined cost and efficiency thresholds. The application areas of their algorithm or methods are high-performance computing systems or parallel computing systems. They use the error rate as the evaluation matrices for their algorithms. Their results found that their elasticity controller can achieve the user-defined target efficiency with only less than 3% error rate, which cannot be achieved using only static resource provisioning in HPC domain. One of the challenges of their algorithm is that their proposed model is only evaluated for parallel research application, which cannot be generalized. Also, depending on users to specify the target efficiency may lead to poor performance due to user errors.
My name is Carl, and I'll be going over some of the papers continuing our review. The first one is measuring effective scheduling intervals against VM load with rapid elasticity. So what this paper really covers is trying to look at different configurations of clusters and how those different configurations yield in terms of execution time under the same job process while changing the amount of hosts, the amount of virtual machines per host, and scheduling interval value. That scheduling interval value is just a fancy word to saying how long each virtual machine should process a job before passing it off to the next virtual machine in kind of like a round robin format. Now, when they did this, what they found was that the startup of new hosts, so if you have a limitation of, let's just say, 3 virtual machines per host, that spinning up, if you pass the need of 3 virtual machines and you need a fourth one, that spinning up of a fourth host really has a huge impact on the total execution time of the jobs. So that definitely skewed some of the results. And what they identified is there's essentially some minimum thresholds for each kind of configuration. And there's this trend that if you have a low scheduling interval, it's best to have a high machine count. So if you say each machine should only be running for the job for 1 second before passing it off, you want a high amount of virtual machines. Whereas if you have a high scheduling interval, saying maybe something like each virtual machine should run the job for 12 seconds before passing it off, then it's best to have a low virtual machine count. And that, again, that comes into that startup time of those servers or those hosts. So next is a paper, Managing Uncertainty in Autonomic Cloud Elasticity Controllers. And what this paper really strives to do is highlight the problems our industry is facing today with the amount of human interaction and the intuition that the sysadmins are just kind of going off of a gut feeling of setting up how the load balancing or the scaling up or the down should be enacted, when that should be enacted, and many times they're manually doing it. So what this paper does is it proposes a new technology. They're calling it a fuzzy controller module, where system administrators would go in, and there's 4 main function areas where they kind of set up a logic matrix, and they're very in-depth going over the mathematical formulas: monitor, analyze, plan, and execute. So these sysadmins go in here, they set up a bunch of parameters, and they're essentially upper and lower boundary thresholds for when more virtual machines need to be brought in to scale up. And what they did is they took 6 real-life simulated loads and they compared their fuzzy controller model on Microsoft Azure servers against Microsoft Azure's auto-scaling server formulas on their own servers. And they found that their fuzzy controller model actually outperformed Microsoft Azure's. So it was very interesting. This is definitely on the side of the upcoming technology. Next would be a paper, Distributed Data Stream Processing and Edge Computing, a survey on resource elasticity and future directions. So as this paper says, it's really a survey, and what it does is tries to address how new the sheer amount of data that's being streamed with the boom of streaming services, particularly some of the big culprits are Netflix and YouTube. Our internet 10 years ago really, we streamed, but not at the amount of sheer data that we did now. And what this paper does is it touches on 10, 15 years ago, this is what the stream processing models were like and how in industry, many of those are still used today, and they're not designed for the sheer amount of data that's being streamed today. It then goes on to touch on some of the upcoming technologies that actually have some kind of promise to be adopted by industry leaders, and how if these industry leaders don't adopt these, they're not going to be industry leaders anymore, and those industries will suffer, and it will actually bottleneck the evolution of the internet as we try to kind of patch these problems as they become issues. Next is Severity, a QoS, quality of service aware approach to cloud application elasticity. And what this does is it proposes a new solution that's really customizable for businesses, because many times if you go to like Amazon, as we learned in class, there's a lot of kind of preset profiles, and what this new approach does is it understands that not all businesses are the same. One business might run a website with these features, and another website runs a different website with a different set of features that may warrant different needs for scalability. And it really tries getting, gives the system administrators of businesses the configuration to really just kind of do the bare minimum to hit a high quality of service, so that their costs are as low as possible and they can maintain that high availability to try to emit as much overhead. Now, this does rely on the system administrators really knowing what do the businesses need and what is the services, what does it warrant and consume in terms of resources. So it's not really going to be good for big corporations, as they are very diversified. It's really good for specialized small to medium businesses. Now, this solution does lock some definitive detail. They don't really go much into like mathematical, computations or anything like that, but it's a high level outline, and the idea is great and can definitely be built upon.
The first paper I will be covering today is Scalability Analysis Comparisons of Cloud-Based Software Services. So to get off, this paper, the reason why it's written is because measurements of cloud scalability and performance are necessary for future optimizations and growth of cloud computing. So to go and measure the performance and scalability, a new metric was created. This metric the new metric basically took inspiration from a previous cloud elasticity measurement and then applied it in the area of cloud scalability. The measurement covers scalability in terms of volume and quality. And tests of this measurement were run in Amazon EC2 and Microsoft Azure. So the following tests were conducted with the metric. It was same software, but on different cloud service providers. Different software with the same provider, so like both on EC2 or both on Azure. And then just measuring its performance with different auto-scaling policies, independent of the provider. So with this, tests were only run with this metric on EC2 and Azure. So to solidify this metric as being fully helpful, future tests should be conducted using other cloud service providers as well to measure its performance there too. And then using this metric. So this paper only really proposes the metric, but they don't talk about how it could be used in the real world, and it hasn't quite been tested for real world applications. So going forward, more tests could be conducted with other providers, and this metric, before it's really solidified as being helpful, should be tested in the real world and used. So the next paper I'll cover is a joint analysis of performance and energy consumption when enabling cloud elasticity for synchronous HPC application, high performance computing applications. So this paper, one of the reasons why it's written is because incorporating elasticity into new applications can be difficult. But it can be helpful too. So metrics need to be created to measure the effectiveness of converting an application to be capable of being elastic and hosted on the cloud. So we need to be able to evaluate elasticity's effectiveness compared to the effectiveness of being elastic to non-elastic. Also in this paper, they developed a model for converting applications to be elastic. That was called autoelastic. And then again, those the metrics comparing elastic and non. This is done in two different ways. A cost function combining runtime with energy models or energy consumption, and one to measure the extension. It was basically an extension of a speed up and efficiency that is commonly used in parallel systems, or that's where currently that metric was used. So a little about autoelastic. It functions at the platform as a service level, used OpenNebula as the middleware, and the model saw good performance, at least that's what the paper said, in terms of converting these applications to support elasticity. So then looking at the metrics that were developed, the application saw better energy results when made elastic. So using that metric with their new elasticity model. So going forward, more tests could have been conducted on these various metrics using other elasticity models and not just the one they developed. This be future proof of these models being effective in the field. And the autoelastic model should be compared with other current models to see how it performs to the other current models out there. And that should be done not just with the metrics and the models metrics that they created, but with other metrics and values too. So now that we have gone over all of our papers, it's time to discuss our conclusion and the findings of all of the current research that has happened in the past 5 years. And the main conclusion that can be drawn is that the field of cloud scalability is at an intermediary level. The groundwork has been laid, but we're not quite at a point where the field is saturated and everything has been discovered. In fact, there's still a lot that still needs to be done in the optimization of current cloud scalability models and processes. So, and as you'll see as we go through the trends, you'll see why we come to the conclusion that it's at an intermediary level. So the largest trend in the papers that we saw was the creation of metrics to analyze the performance of cloud scalability models. And going that kind of comes hand in hand, and if the first subthread there, new architectures are still being proposed, but not too many. So probably in the past 5 to 15 years, a lot of new architectures came out and cloud's computing became far more popular. And now at this point in time, we're currently working, or the field is currently working to find ways to optimize these models. So now that we have created a lot of architectures, we're now seeing less new ones being proposed, and we're now finding new ways to analyze these models and compare them to each other and ways to optimize them. So that was like the biggest trend we saw overall, was just new metrics. Some other smaller subdomains that we saw was basically the automating the creation and maintenance of scalability and elastic models. Kind of goes putting them into a common framework, kind of goes hand in hand with that. I didn't have a good way to display it. Those kind of go together. We found that as one category right there. And then also another subdomain was finding methods for preparing current other domains for a scalable architecture. So finding ways to apply elasticity and scalability, like put different current domains onto the cloud, and finding these niche domains that don't fit the current cookie cutter or current models or methods of doing scalability and elasticity, how we go about adapting those. So that was small for that. So now we go into what we expect now in the future, knowing these what the current research was and where we see as where the current research is lacking. So now that we have seen the emergence of many new metrics in the last 5 years, a lot of testing now needs to be conducted on these metrics. These metrics need to be benchmarked on multiple different models. Different models need to be analyzed with these metrics. A standard set of metrics is most likely to emerge sometime in the near future. As right now they're just being produced, and that seems like the natural flow of things. Once that standardized set of metrics has been decided, we're also most likely going to see an optimization of the current models with these new metrics. Currently, models cannot be optimized further as there is no clear way to optimize them if you do not know a clear way to measure how they are performing. So really, it's figuring out that performance, like we said, was the biggest thing seen in the last 5 years. So going forward, it makes sense that we will then see more work to be done on what are the best metrics. And of course, as the field then becomes more mature, we're most likely also going to see more research done and more papers published, preparing these more niche domains to be able to be run on a cloud or architecture, a scalable architecture.
Thank you for taking the time to watch our presentation and learn about the papers we covered. If you have any questions about our presentation, please don't hesitate to message us as we'll happily follow up. Thank you again for your time.